It may look like an oil rig, but this is actually one of the world's first engines. This machine is the genesis of the genealogical tree of modern technology. Airplanes, power plants, trains, cars, and even refrigerators owe their invention to this innovation, the Newcomen steam engine. Thomas Newcomen was born in Devon, England, in 1664. He was a merchant of cabin goods and a preacher, determined to find the way to solve the problem of flooding in local mines. It turns out that Newcomen's steam engine is not only a direct ancestor of modern engines, but its invention in 1712 helped lay the groundwork for the rise of machinery, leading to the Industrial Revolution. Had this machine not been designed, the technological tree of our society as we know it might have evolved differently, and our world would be unrecognizable. So let's explore this ancestor of all engines and see how it works. The Newcomen steam engine resembles an oil rig because it serves a similar function. Oil rigs pump oil from the ground, while the Newcomen steam engine was used to pump water out of mines. Let's look at this engine in action. It seems slow, doesn't it? But it was the first of its kind. So operating at 12 cycles per minute was quite fast. On one side, we have the steam engine, and on the opposite side, a pump that draws water from the mines. Above is a heavy wooden beam and a pivot point that swings like a seesaw, with arched heads and chains transferring motion from the steam engine side to the pump side. But the revolutionary part was the steam engine itself. So let's focus on it. Here we have a piston, a cylinder, a boiling tank with fire underneath, a water tank, and a set of valves. To start the cycle, the weight shifts to the pump side, pulling the piston upward. As this happens, hot steam fills the cylinder, and once the chamber is full, two valves close. Then a valve quickly opens to inject water into the cylinder, and the jet of water cools the steam. Then a valve quickly opens to inject water into the cylinder, and the jet of water cools the steam, then the valve closes. This cooling causes the steam to condense from gas back into liquid, and as a result, the pressure inside the cylinder drops sharply, creating a vacuum. With atmospheric pressure pushing down on the piston and vacuum inside the chamber, the piston descends, generating energy. This energy is transferred through the beam and used on the pump side to extract water from the mines. This part of the cycle is called the power stroke. Now that the piston is down, the cycle resets, and the two valves open. The vacuum breaks, steam rushes back in, while the condensed liquid water exits, and the cycle repeats. The top, the steam, and exhaust valves close. The water valve briefly opens, and the jet of water condenses the steam back into liquid, again creating a vacuum. The piston descends, two valves open, the vacuum breaks, steam enters, and condensate is removed. Now wait. Let's pause the cycle and take a closer look at the steam cylinder to better understand how it creates enough force to move the massive wooden beam and pump water. To do this, we'll zoom in to see how the molecules move. At the bottom is the steam cylinder, in the middle the piston, and above it atmospheric air. Steam and air particles move, and each time a molecule hits the piston, it transfers a bit of force. The force from air particles hitting the piston is called pressure. The force exerted by atmospheric particles is atmospheric pressure. So at this stage of the cycle, the piston is at the top of the steam-filled cylinder just before cold water is introduced. The movements of atmospheric and steam molecules are balanced. Now, as water is added to the steam cools, and the motion of steam molecules slows. As movement slows, intermolecular bonds begin to form. Simply put, the steam turns from gas into liquid. This liquid forms droplets, falls to the bottom of the cylinder, and collects there. Now there's a force imbalance. The atmosphere still presses down on the piston, but with the steam condense into liquid, there's no longer counteracting pressure beneath the piston. The lack of upward force means the piston is now pushed down by atmospheric pressure. This absence of pressure is called vacuum pressure. Technically, it's a partial vacuum, since the cylinder wasn't completely emptied of steam. Nevertheless, enough force is generated to move the piston and operate the pump. That's why the Newcomen engine is called atmospheric. It uses the atmosphere to do work, and the steam pressure inside the cylinder never significantly exceeds atmospheric pressure. Familiar steam engines use high-pressure steam, sometimes hundreds of times greater than atmospheric pressure. But in the early 1700s, vessels capable of withstanding high pressure were unreliable and prone to explosion. Now let's move on. So now that we understand the concept of creating a vacuum, let me ask you, if I took 1 liter of liquid water and heated it into steam, what volume would that steam occupy under atmospheric pressure and without compression? Maybe 10 liters. 100 liters. 1 liter of liquid water converted into gas occupies nearly 1,700 liters. That's a crazy expansion. Here's a 2-liter bottle of water. Let's boil it. The steam will fill much more space than 4 large refrigerators. Now let's reverse the process. Start with a massive 425-liter steam tank under atmospheric pressure. Cool it down, and the gas turns into just a bit more. Then a glass of liquid water. You can see this in the steam flow as it condenses. Thomas Newcomen understood this concept and how to build this engine to pump water. This innovation was revolutionary and gave rise to an entirely new technological tree. Although the idea of combining metal, water, and fire existed since ancient times, only in the 16th to 17th centuries did the understanding of vacuum and pistons improve enough for Newcomen's revolutionary idea to emerge, combining fire, steam, pistons, and vacuum in a cyclic engine for continuous operation. The Watt steam engine was invented 60 years later. It became more efficient and the true workhorse of the Industrial Revolution. But James Watt got his ideas while working on Newcomen's steam engine. In the 1800s, high-pressure steam engine designs powered boats and locomotives, and eventually steam was replaced by the internal combustion engine. But none of these engines would exist without the foundational work of Thomas Newcomen. His ability to creatively combine technologies around him changed the world forever. Stay tuned for new branches in this series, where we'll explore traction engines and dive into the details of how steam engines work. Thanks for watching. Don't forget to subscribe, like the video, leave comments with your questions and thoughts, and share what you learned today with your friends and family.